Hi there. Today we're looking at When Bert Plays the Lottery, All Tickets Are Winning by Sai Prasanna, Anna Rogers, and Anna Rumshisky. So a high-level overview of this paper is the following. The paper basically looks at Bert in terms of the lottery ticket hypothesis. And it says that if you fine-tune Bert on different downstream tasks, then the lottery ticket winners you're going to find are different between the task. And also, the claim all tickets are winning refers to the fact that if you remove the winning tickets, then you can still train the rest to relatively good performance. Therefore, all tickets are winning, not just the subnetwork. So that was the high-level overview for those of you who just want to be interested if you want to continue watching this video. If you do like videos like this, consider sharing, liking, subscribing, telling your mother, father, brother, and friends about it. All right, let's dive in. So, Bert. It is a language model. Basically, if you don't know what Bert is, I've done a video on Bert, but really quickly, what you can do with Bert is you can take a sentence, something like hello there, and you can put it through this multi-layer neural network, and what you'll get out is basically an embedding of that sentence. So a vector embedding of it. We'll make it really easy. And what is usually done is this is pre-trained on a task called masked language modeling. This is unsupervised training. And then you take this embedding and you fine-tune. Basically, you put on a classifier head. You basically say, let's take sentiment classification. So you have two output classes, and you want to say, is this sentence I put in positive or negative sentiment? So you would train this classifier by basically taking this part from the pre-trained masked language modeling and then training the part here that does the sentiment classification. You would sort of add that on top and then fine-tune the entire network to solve this task. Right, so that is basically Bert fine-tuning on different tasks. And there's this benchmark called GLUE, where it has a number of tasks. In this case, I think they look at 9 tasks of GLUE. It has 9 of these tasks. One is an example is the sentiment classification, and it basically gets a score for each one, and thereby you can sort of estimate how good your language model is by how well it is performing on each of those individual tasks. But the notable difference here to, let's say, a computer vision, like an ImageNet classifier, is the fact that first it is pre-trained, right? This part here is pre-trained on a large corpus, and second, there are different downstream tasks that you fine-tune on. So, the second part that is important is the lottery ticket hypothesis. So I've also done a video on the lottery ticket hypothesis, and if you, very quickly, what the lottery ticket hypothesis is the following. So let's say you have an image classifier, and I have a bunch of layers in my neural network. I'm going to draw them like this. And at the end, right, I can classify it into like 10 different or 1,000 different classes, whatever. And the input here is an image. So my neural network is going to have weights. So every one of these neurons is connected to each other. Now this can be a convolutional network or a MLP. So all is connected to all, and as well here, right, everything's connected to pretty much everything. So we know, first of all, we know that we can train these big networks to relatively good accuracy. And then second of all, so first we can train them. Second, we know we can prune them after training. What pruning means is the fact that after I have trained such a thing, I can then go and I can figure out which of these connections that I have learned are the important ones. And maybe I'll say, these here, actually these 5, I don't need more than those. Let's actually connect them to the end. These 7 or so. I don't need all of the other ones. I just need those, and I can pretty much get the same accuracy as the full network. Now, the important part here is that you can only do pruning after you've trained a network. If you try to prune at the beginning, it doesn't work. So what the lottery ticket hypothesis says is basically, so how does training work? First, you have your parameters. Let's tell them as a list. So each of these weights is an entry in the list here. First, you initialize these randomly. Then through training, you get to your trained state, right? You get each of the ones into your, these are now trained. And in the trained state, you can select the ones you think are important. The lottery ticket hypothesis says, if I take those that are important and basically go back to the beginning, like here, here, and here, and I basically roll them back to that state that they were in when they were initialized. So I put the same random number there that I got at initialization. I can then make a network where I only have those. I can train that network, and I can get a good accuracy. So this basically wasn't possible in the pruning framework, because we said we can't prune. We can only prune after training, because only then do we know which ones are the important ones. In fact, the lottery ticket hypothesis, or the paper, shows that you can train the smaller neural network from the beginning, but the catch, of course, is you have to know which ones those are, and you have to know what value to set them on at the beginning, and you only know that after you've trained the full network. But still, it kind of gives the it tells you that you don't need all these connections for training. You basically only need so many connections such that somewhere in there there's going to be the good ones, right? And if you knew the good ones from the beginning, you could just train those and then only train the smaller subnetwork. So that's the lottery ticket hypothesis. Naturally, these connections here, this small network is called a winning ticket, because if you knew what it was, you could basically train a much smaller network and reach the same accuracy. So this paper looks at BERT in terms of this lottery ticket hypothesis. Now, it's a bit more complicated than just in these feed-forward networks, because BERT is not a feed-forward network. BERT is a transformer. So what does that mean? A transformer consists of many layers, and each layer, let's expand the layer here. So each layer consists of, let's go over there, need some space. So again, we have our layers of BERT, and the signal goes like this. So each layer consists of two things. First of all, of many attention heads, that's called. And I'm going to draw these as blocks right here. So let's call them 4 attention heads. Individual attention heads are all parameterized by individual matrices. And then on top of that, there is an MLP. So this is the multi-layer perceptron. This is one, basically a feed-forward layer, residual actually. And so there is a skip connection right here. And these are the attention heads. Okay. And then the next layer would again have the same structure, 4 of these and then 1 of these, and so on with the skip connection. All right, so the pruning in BERT is different than pruning in the feed-forward or convolutional neural networks that we looked at. Pruning in BERT, what this paper looks at, is pruning either an entire attention head like this, so kind of leaving out in the entire head away, this is an entire matrix. This is not a single weight, right? This is many, many weights. Or even more drastically, leaving away an entire MLP and basically only relying on the skip connection. All right, so this you have these two things you can do. You can leave away heads, or you can leave away entire MLPs, or you can combine these things in some way. Right. So the notable difference here to the lottery ticket hypothesis pruning is the fact that here, up here, what we prune are connections. So prune connections, individual connections. And here we prune entire modules. Now this is in my opinion, this is a qualitative difference, a very large qualitative difference, actually. Why would you do this? So this paper basically doesn't invent this kind of pruning. They go after already existing literature. So what's the advantage in pruning modules? Well, you have to see what's the advantage in pruning per se. So in pruning, what you're trying to do is obtain a smaller network that gives you the same accuracy, but that you can run faster, right? That it uses less memory, and you can run it faster. And if you prune like this, like we did in the lottery ticket hypothesis paper, you don't really gain anything, because if you have a matrix, matrix multiply, right? I have two matrices and I multiply them right here. If I cut out one weight here or one weight here, that doesn't help me, because I have GPUs and those will parallelize these matrix procedures, and it doesn't really help me because we don't really have good hardware for sparse or matrix multiplication, or matrix multiplication with holes or things like this. So it almost gains me nothing. The lottery ticket hypothesis paper is very much a kind of more of a scientific curiosity paper, and once we have sparse matrix multiply hardware, which I think it already exists but is not super widely distributed, once we have that, we will be able to make use of this. Whereas the people that prune BERT, so these are more, let's say, industry people, if you prune an entire module, well, that's an entire matrix that falls away. So I can basically save an entire matrix multiply in the forward pass here and the backward pass. Well, okay, I don't prune during training, but I can basically save an entire matrix multiply here by pruning an entire module. So I'm not sure if I were an author and I say I want to look at BERT in terms of the lottery ticket hypothesis, I would find a way, I would go away from this literature and find a way to also just prune here individual weights. It's not going to be faster, but the lottery ticket investigations aren't supposed to be faster. They're supposed to tell you something about the nature of the things you're investigating. And of course, how you do this is simply by masking, right? You simply force these entries to be 0, and therefore you don't have forward signal, you don't have gradient. Interestingly, they actually do the masking, but they do it on the whole entire module level. Okay, so this was BERT and the lottery ticket hypothesis, and the all tickets are winning we're going to investigate later. Let's see what they say in the abstract. Say, much of the recent success in NLP is due to the large transformer-based models such as BERT. Okay. They say, however, these models have been shown to be reducible to a smaller number of self-attention heads and layers. So this would be pruning. We consider this phenomenon from the perspective of the lottery ticket hypothesis. For fine-tuned BERT, we show that, here's the contributions. A, it is possible to find a subnetwork of elements that achieves performance comparable with that of the full model. So basically, this is the pruning objective, right? You want to prune it such that the performance holds, and in terms of the lottery ticket hypothesis, you want to prune, reset to the beginning, and then train again, and that will give you, actually in the lottery ticket hypothesis, you can gain performance if you prune by a certain amount. In this case here, they always lose performance, but yeah. So second of all, similarly sized subnetworks sampled from the rest of the model, so the non-winning ticket, perform worse. So if you just prune away the good parts, then the bad parts perform worse, of course. However, the bad subnetworks can be fine-tuned separately to achieve only slightly worse performance than the good ones, indicating that most weights in the pre-trained BERT are potentially useful. So this is interesting. If they be fine-tuned separately, this is exactly what the lottery ticket hypothesis is doing, right? It's basically fine-tuning only a sub-part of the network. And here they say, even if we take the parts of the network that have low scores for pruning, and we retrain those, then we can achieve a good performance. Okay, so they say we also show that the good subnetworks vary considerably across glue tasks. This is this benchmark, opening up the possibilities to learn what knowledge BERT actually uses at inference time. All right, so this is the overview of the paper. So a last thing to say, which I've already kind of alluded to, is the fact that in the original lottery ticket hypothesis, as I said, you had a graph and you had some sort of, here was 100% accuracy and here was how much you prune. Of course, you start at 100% if you prune nothing. But then as you prune, the interesting thing is it kind of goes up and then it goes down, right? So this is the first thing here, it goes up to a certain amount if you don't prune. And in the original lottery ticket hypothesis here, somewhere here would be 50% of the network, I think. And then once you go down, let's say here, to 90% of performance, you are at something like 5% of the network size, or 3%. So you can prune away most things and still be like extremely powerful. Now we're going to see what essentially what these people do here. Here is 100%, and they simply prune until they reach 90%. So we don't necessarily know what happens in the middle. We just know they start here and somehow they get to 90%, and what they end up with is something like 50% of the network still remaining. So again, see the qualitative difference here between the 5% of the lottery tickets in the original paper and the 50-ish or so percent, or considerable amount more in this paper right here. And I'm pretty sure that is due to the fact that they prune entire modules here. So they don't prune on a fine-grained enough level to investigate these phenomenon. Because, as I said, we don't know, but I'm pretty sure this just goes down here and not up first. So qualitatively, it seems different. All right. So here they introduce what they do. Again, BERT is made up of these attention heads and MLPs. The MLPs have a skip connection, as you can see here, and the attention layers are basically made up each of n of these attention heads. What they will do is they will look at 12 layer networks. Each layer will have 12 of these attention heads and 1 of the MLPs. So you have in total 144 heads and 12 MLP layers. The way they determine which ones to prune is pretty easy. In front of each attention head and in front of each MLP, they put one of these binary variables right here. These variables can take values 0 or 1. If they're 0, the layers or the head is basically inactive, no propagation. If they're 1, they're active. And they determine what value to set them to by computing importance scores, basically determining how important is a head or a layer for the network. And that's pretty simple. You simply take the gradient of the loss. I think they go after this paper right here that propose the following. You derive the loss by these variables right here, and therefore you get these importance scores. And then you can simply prune the layers with the lowest importance scores, because that means that the gradient with respect to them is the smallest. That means your loss changes the least if you were to leave them away. Okay. So they here determine their pruning strategy. Their constraint here is, as I said, 90% of the performance of the full model. So they train the full model, fine-tune the full model on this task, and then they set themselves a budget of 90%, and they simply prune until the model reaches 90%. Once it goes lower, they stop. Okay. So they have 3 methods of pruning. One is heads only, where they only cut away these attention heads. As I said, there are 144 of them. They have the pruning strategy of MLPs only, where they only prune the MLPs, leave all the attention heads alone. And they have this heads and MLPs. They say we compute head and MLP importance scores in a single backward pass, pruning 10% heads and 1 MLP with the smallest scores until the performance on the def set is within 90%. Okay. Then we continue pruning heads alone and then MLPs alone. And this, I guess, until, again, they are no longer in the 90%, so until they reach their budget. So this is a combined strategy. This strategy results in a larger number of total components pruned within our performance threshold. So this is the thing we should focus on, right? Because in pruning, the name of the game is how much can you take away and still be within your budget. And this strategy seems to be the viable strategy here. So a last thing here is fine-tuning. So the other difference between this paper and the lottery ticket hypothesis is that we said that in the original paper here, these are randomly initialized weights. Like you train a class for an ImageNet or something, you start from randomly initialized weights, and the lottery ticket papers, they all kind of presuppose random initializations. Whereas BERT, when you do the same thing for BERT, these are not random initializations. We said in BERT, what you usually do is you train the encoder part here, you pre-train with masked language modeling first, and then second, you train the entire thing. Let's get the color here. Second, you train the entire thing. You fine-tune the entire thing. So if we talk about initializations in the BERT task, then the initialization would be at this point right here, after the masked language modeling would be the initialization. So the weights are not random. The weights are actually pre-trained on the masked language modeling task, which is also a qualitative difference and sort of lets us inspect. So the authors say that since we trained with masked language modeling and people sort of claim that masked language modeling learned something about the language, we can now investigate kind of which attention heads, which modules in BERT are encoding which parts of the language. And this is going to be interesting once we look at which heads, which attention heads and which modules survive in the individual tasks. We can sort of compare tasks across each other by seeing which of the heads they share in their winning tickets. All right. So they produce these graphs here. These are sort of one of the central graphs here. And the way to read this is on the left side here, you have the layer. Whoops. You have the layer index. And on the x-axis, you simply have the index of the head. There are 144 boxes here. Each one corresponds to one of the attention heads. The top number is always the mean number of glue tasks that this head survived in. So what they do is they take the pre-trained BERT, they fine-tune it on these 9 tasks, and for each of the 9 tasks, they determine the winning tickets, right? And the number here says how many of these 9 tasks is this particular attention head a part of the winning ticket. Now they repeat it for different random seeds, that's why you have floating point numbers, and the lower part is the standard deviation across that. So you can see quite a number of heads make it into a lot of these tasks. So you can say this part, this thing right here, red on red, this head right here survives in 7 out of the 9 tasks. So it should be it probably encodes something fairly substantial about language that is shared across these 7 tasks, right? You can see some of the heads, like this one here, doesn't survive in almost any task, which basically means that it's, that one's not really super important for these tasks. It might have been, important for the pre-training, but not for these particular tasks. What's interesting, so what you can see is that the mean or median or so is like 3, 4, or 5. And that means that a lot of the heads are sort of somewhat important for some of the tasks. And you can see the qualitative difference. If this were the original lottery ticket paper, most of these numbers would be at 0 because the lottery ticket size is just so much smaller. Here you can directly see that you are going to retain a large number of things in your network in order to get 90% of the performance. And that's probably because you prune entire modules again. So they have this for 2 variants here. First for the strategy of masking heads only, and the right one is for masking heads and MLPs. And the same here on the bottom. These are the same numbers, but not for attention heads, but for MLP layers. And you see again, this is masking MLPs only. This is masking heads and MLPs. So if you compare the two, you see that, for example, this here and this here are substantially darker, which means more of this stuff survives. Now, we can't really, it seems like here, for example, it's darker than here. So on the right side, more stuff survives, but also you have more things to prune, right? You have, you can prune the heads and the MLPs. And they claim before that the masking heads and MLP strategy results in more things being pruned, which isn't really congruent with here generally more things surviving. But it could be because of the fact maybe the sum of the two is still lower than the sum of each individual thing here, though it doesn't really look like it. So I'm a bit confused about this, but I'm just going to assume that the sum of the two is lower. Does that make sense if both are darker? Well, it shouldn't be the sum. It should be the sum of this plus a completely dark this in terms of masking heads only, or vice versa, versus the sum of those two, right? So that should be the measure. But it just seems a bit doesn't work out too much. But okay, that's what they say. So by the way, if the authors are here, you have this is cut off. Yeah, this is annoying. This is like trying to get LaTeX to do things, and it doesn't comply. All right, so another thing you can see, and the authors point out here, is that if you mask heads and MLPs, you sort of shift more things to the back of the network, to the higher up layers. And they reason now because you also mask the heads, basically they can't do as much work. So so the heads would be masked somewhere here. So all that work is going to shift upon the MLPs and mostly to the back of the network, because this thing here cannot take over work that this attention head here is now not performing anymore because it was pruned, because the signal travels this way. So the authors kind of interpret these results right here, and I think the most important thing to see is simply the variance of things. So most heads are actually important for at least 2 or 3 tasks, and no head is important for all the tasks consistently. I think that's the take-home message right here. Okay, and they contrast this to previous research that has basically said this experiment follows up on a study by this that showed that only a few transformer heads in machine translation tasks did the heavy lifting, while the rest could be pruned. And this paper similarly showed that most of Bert's self-attention head in MNLI task could be pruned, and that the good heads were mostly shared between the MNLI matched and mismatched. And they basically say, yeah, that's correct, but that is only within one task, right? If you go beyond, if you go to several tasks, then the heads that are important differ quite a bit. Okay. So let's continue and go here, they ask how task independent are the good subnetworks. And they basically look at these kinds of graphs right here, which are pretty interesting. So we'll go at this. This is heads shared between tasks. So what this measures is, these are the different tasks in the GLUE benchmark. And they basically look at each task, look at its winning lottery ticket, and look at which heads survive in the winning ticket. And then they put that here on the diagonal. So if in QNLI a head survives, it gets a 1 here. And if it doesn't survive, it gets a 0. So on average, 85 out of the 144 heads survive, right? 85 heads survive. That's pretty, as I said, this is somewhat like over 50% of the network. It's entirely different than the original lottery ticket hypothesis paper. So 85%, not percent, 85 of the 144 heads survive. Now they look at the other tasks. So for QNLI, they would look at maybe MNLI task here and ask which of the heads that survived in QNLI also survives in MNLI. So that gets you the shared heads. And again, the lower number is a standard deviation. So 62 heads survive in QNLI and MNLI. And the authors here are sort of arguing that from these sort of numbers, you should be able to see which of the tasks share different linguistic knowledge. So different linguistic knowledge could be relevant for the for different tasks. But if some tasks share a lot of the attention heads that survive in the winning tickets, that basically means that the model is using that information that is in that head for both tasks. This could be good in that you say, oh yeah, these tasks really use similar linguistic features, or it could be something that you don't expect, and then you might be able to investigate, maybe the model is doing something shady here, because it really shouldn't, you know, these tasks don't really have much in common. So they do this for the heads and the MLPs here. Now, if you ask why the WNLI here has a bunch of zeros, that's because it's a wonky task, and basically the best thing you can do is predict the most frequent class. So you can prune just about anything away on these MLPs because they have the skip connections. You don't need them to predict the most frequent class. What I want to go into is the following statement right here. Note that figure 1, so the figure before, shows very few heads or MLPs that are universally useless. Only 7 heads that survived in less than 2 tasks. 86% of heads and 67% of MLPs survive in 2 to 7 tasks with relatively high standard deviation. They say this means that the good subnetworks for different tasks have relatively little in common, right? So they make this sort of statement again here that the good subnetworks have little in common, and it might seem like that for the figure initially, but if you look in this figure, it actually shows something pretty interesting, I think. So if you look at a number, let's say, for example, this here, this 74, and I haven't actually tried. Yeah, let's look at the 74 and this here. So let's look at these tasks: Q, QP, and RTE. Okay. So if you look at QQP and RTE, you could see that these are tasks that already they don't have a lot of heads in common, right? And you might be able to say, well, if what they're saying is true, that the tasks share relatively little, you would expect them to be relatively independent. But if I look at this 78 here, it means that 78 out of 144 heads survive. And here, it means that 74 out of 144 heads survive. So if I now would think that, okay, generally for different tasks, things are different. How many heads would I expect there to be surviving in both if the tasks are independent? So that's these two things multiplied, right, times 144. So I can scratch this here, and the 7 times 7 is whatever, 49. Let's go 7 times 8 about this. So that's 5, 6. Do I need to get out a calculator? I wanna do this calculator. Shugabing. I'll do this the right way. Okay, I hope you can see that. So that's 78 times 74 divided by 144. Did I do it right? I probably did it wrong. 78 times 74 divided by 144. All right, so that's 40 heads. And you see that there's 43 heads. And I've actually gone through a bunch of these numbers before, not these ones, but generally the shared number of heads is higher than what one would expect if you assume that the tasks are independent. And I'm sort of missing sort of an analysis of that here, because that I find to be a pretty interesting finding of these things, and sort of I mean, I get the fact that they say, based on the graphics up here, that the tasks are seem to be relatively independent with respect to the heads that survive. And of course, relatively independent is a relative term, but it's sort of an investigation into why we see considerable dependence between tasks here in terms of that. So these numbers are always over what you would assume for independence. That seems to be pretty interesting. All right, so they say, they here go into this figure 2 and this pairwise comparison, and they analyze a couple of the different tasks here and what you would expect. And I don't want to go too much into these tasks, because honestly, I also don't know all of these tasks. I don't know which tasks should share a lot of things, which ones shouldn't, but it is a good way, like it is a very smart way to investigate if the model really learns similar tasks to use similar information. All right, the last thing they do right here is the good and the bad subnetworks in BERT fine-tuning. So they say our final experiment puts the above evidence of good subnetworks in BERT fine-tuned from the perspective of lottery ticket hypothesis, which predicts that the lucky subnetworks can be retrained from scratch to match the performance of the full network. To test this hypothesis, we experiment with the following subnetworks. So that means I wasn't really sure when I read it the first time, but now I'm fairly sure that all of the results so far were just pruning and maybe not retraining. So just sort of doing the pruning thing and not doing this lottery ticket retraining, which shouldn't make a lot of the difference, as we're going to see, but just for the understanding, because it seems like pruning and retraining doesn't do that much for the winning tickets, as you'll see right now. But yeah, so now they actually retrain from scratch. So good networks, the elements selected from the full model by importance scores as described in the previous section. So here they're going to evaluate these good networks. First of all, they're going to evaluate them pruned, and they're going to evaluate them retrained in the lottery ticket style. Okay. Then they're also going to evaluate bad subnetworks, the elements sampled from those that did not survive the pruning, plus a random sample of elements with high importance score, so as to match the size of the good subnetworks. So because the good subnetworks are 50% or more of the network, they're going to sample from things that did not survive, so from the bad ones, and they plus a random sample of the good subnetworks to just match the size. Okay, so we would expect these to perform maybe worse, but maybe we can also train them to achieve good performance. And then they investigate bad subnetworks, simple inversion of the good subnetworks. So these would be just anything but the good. They are 5 to 18% smaller in size than the sampled bad subnetworks, but they do not contain any elements with high importance scores. And they say, okay, for all of them, they evaluate their performance on all tasks simply after pruning and with fine-tuning the same subnetwork with the same random seeds and with the rest of the model masks. So this is really what the lottery ticket hypothesis does, except they, of course, mask entire modules and not individual weights. And here you can see the general results. So the general results look like something like this. This is a typical example. So this is the, let's go out. Oh yeah, this here is simply the dumb classifier that always tells the highest probability class. This is the this is sort of the idiot's baseline, okay? This here is the full model, full. This here is the good pruned, and this here is the good after it's retrained again, okay? So you see by retraining you can basically gain. Now in the original lottery ticket, this would sometimes even go up here depending on how much was pruned, but you can see that there is a slight gain after you retrain the pruned part. Okay, and the other thing to note here is that you don't lose much. Basically, you only drop a little bit by pruning, which that's what makes it the good part. You only drop a little bit. However, if you have the bad part, which are these, and let's say the good plus bad. These are the bad plus some of the good ones. You see that the performance drops pretty heavily, almost to the baseline of the most frequent class, and also here. So I would go with this one right here, because that's just the bad ones. You see the performance drops considerably, but then, and that's what the authors claim is pretty interesting, if you retrain that part, the bad part, so to say, you can achieve sort of a very comparable performance to what you can achieve with the good parts. And this appears to be true for most of the results right here. There are some outliers like this one, but the score is also, so this is the Matthews correlation and not the an accuracy. So the score is a bit different there. But you can see here the good plus bad also gets a fairly high accuracy. All right, so the authors claim this is pretty surprising, which I guess it is if you look at this. But what I want to do is I have asked the author of the lottery ticket hypothesis this question. So this is from our machine learning street talk with Jonathan Frankel. And this is another channel that I'm a part of, and I would like to show you this right here when I asked him this question.
Another question from Reddit, Imnemo asks, suppose you try to construct a lottery ticket by taking all the weights that were not part of a winning ticket and retraining from those. Will that model be unable to learn the task? Or might there be another winning ticket hiding among them, or one that wasn't originally used?
So this is the most common question I get by people who read the original paper, and I hope that by answering it here in a public forum, I can answer it once and for all. The challenge in doing this experiment is, let's take the MNIST example. So suppose that we find a winning ticket on MNIST. It's going to be about 3% of the original size of the network. So that means that if you remove it, you've still got 97% of the weights left. And so my guess is that if you were to train those 97% of weights, you'll get to the same accuracy as you got with 100% of weights, because you've barely pruned the network at all. You could randomly prune by 3% and it wouldn't affect it. And then you could go and find another lottery ticket that's mutually exclusive with the first. You still have 94% of the weights. And you could probably iterate this for a very long time. Probably, you could probably this way find, 10, 15 lottery tickets like this, maybe more, that are all mutually exclusive and still leave you with a remaining kind of residual that is capable of training to full accuracy. So the challenge with this experiment is that the lottery tickets are small, which is great, but it means that whatever's left is large enough that, you know, I'm sure there's another lottery ticket in there and another lottery ticket in there, and so on and so on and so on. So it's an interesting idea in principle, but once you kind of look at the sizes of things, you've still got so much overparameterization left that I think you just find more lottery tickets. You can even probably, I'm guessing, swap out one weight from a lottery ticket with another weight, and it wouldn't matter, or swap out a handful of weights. And so combinatorially, the number of lottery tickets is massive, and we're just finding one.
All right, so as you saw, this is kind of the most common question that Jonathan gets here. And as you can see, the difference here, of course, is that our original tickets are already sort of 50% of the network. So what's left is only 50%. So this is substantially different. Now, two things I have to remark here. First of all, because we are pruning modules and not individual weights for the good one, it's the reason that we do get these big winning tickets, right? But also what I think is happening is that because we are pruning these entire modules, we're actually not fine-grained enough. So that means every time we eliminate a module, we actually kill some good ones and some bad ones. And so in here, I'm going to guess there are some good ones and there are some bad ones. But since we can only kill entire modules, you know, we sort of we simply kill the one that on average has the most good ones. But I'm guessing that in the thing we kill, we kill the one that has on average the least good ones, but there are still some good weights in there. And if you believe the original lottery ticket hypothesis, that means that these very few weights in those modules can still train to full accuracy. So what these authors claim is surprising in light of the original lottery ticket hypothesis. I think if you look at it from the perspective of the actual hypothesis, which considers individual weight and a very small subset of them, the original hypothesis would pretty much predict that you could train something where you pruned away a bunch of modules entirely, or you could train these bad modules because they are still going to contain a small-sized lottery ticket that is going to be responsible for the good performance. So that's the kind of the first thing. And the second thing, in general, you heard Jonathan, I don't think that is actually even a question of the size of the tickets. Nothing in the original hypothesis forbids the non-winning ticket from also being trained to good accuracy. It simply says something about the winning ticket. It doesn't say anything about the non-winning ticket. So those are the two comments. And I think the question and the investigation, even though it is interesting, I think is sort of maybe not thought through, at least in the perspective of what they go for here. I mean, the result is very interesting, but again, I think they claim the original hypothesis would sort of say these are the bad parts and you couldn't train them, and then they say it's surprising that you can. But I would say that the original hypothesis would in fact predict that you could train those things because you've pruned away these entire modules, which is very coarse-grained, and that leaves still good weights in the bad parts. Okay, so they conclude, however, we can see that both good and bad networks can be retrained with comparable performance for many tasks. The inverted bad networks perform worse than the sampled ones, but that could be due to them being smaller in size. Performance of all inverted bad networks on call is almost zero. Okay. Yeah, okay, very little remains when that mask is inverted. That's the task we looked at because they claim, yeah, that's so small, which makes sense, right? So discussion. Say, does BERT have bad subnetworks? The key result of this study is that as far as fine-tuning is concerned, BERT does not seem to have bad subnetworks that cannot be retrained to relatively good performance level, suggesting that the weights that do not survive pruning are not just inactive. However, it is important to remember that we consider elements of BERT architecture as atomic units, while the original lottery ticket work relied on magnitude pruning of individual weights. So they're well aware here of these differences, and they concede to that right here. So that's good. On that level, BERT probably does have bad subnetworks, and they show that can be found in the transformer model with global iterative pruning. We leave it to future research to find out to what extent the effective subnetworks overlap with the effective architectural blocks and what that says about the architecture of BERT and the other transformers. So as you see, that they're well aware that that all of what I said is the case. So it's not like I'm criticizing and saying they're wrong. It's just that if you read it, you sort of get the impression that this is what they're saying, and I think the light of which a reader goes through it is just a bit such that you come off, if you don't read until here, you come off thinking something else. Our results suggest that most architecture blocks of BERT are potentially usable in fine-tuning. This should not be interpreted as proof that they all encode potentially irrelevant linguistic information. That's absolutely true, yeah. It is also possible that pre-training somehow simply made them more amenable to optimization, which is another question for future research. And they go into what do different BERT components do in the different things. So again, I think this work here is actually most relevant for investigating this question: what do BERT components, the different BERT components, do for the different tasks? To look which tasks use which things, and the actual recognition that none of these modules is useless. I would consider pretty cool finding. Okay, so in conclusion, they say prior work shows that it was possible to prune most self-attention heads. We extend this to the fully connected layers. We show fine-tuned BERTs as good and bad subnetworks, where the good heads and MLPs alone reach performance comparable with the full network, and the bad ones do not perform well. However, this pattern does not quite conform to the lottery ticket hypothesis. Both good and bad networks can be fine-tuned separately to reach comparable performance. We also show that 86% of heads and 57% of MLPs in good subnetworks are not universally useful. Across glue tasks and overlap between good and subnetworks do not necessarily correspond to task types. So that's where we didn't go into. This raises questions about the degree to which fine-tuned BERT relies on task-specific or general linguistic knowledge, and opens up the possibility of studying the good subnetworks to see what types of knowledge BERT actually relies on at inference time. So this is sort of future research direction. And with that, I think we've gone through the paper. I hope you got something useful out of this. I think it's a pretty cool paper. It's a pretty cool methodology. And I think a lot of work can build upon this to do interesting analysis of these language models. Again, if you like this video, consider sharing it, subscribing, liking, and bye-bye.